Alright, so today our video is going to be on interest rate swaps, and I want to focus more here on the pricing mechanism of interest rate swaps. And so this will be a little more technical of a video, but hopefully you can follow along with the math formulas here. And interest rate swaps just in general are a very popular market derivative. They are basically really used to swap. It's a transaction between two counterparties, and you're basically swapping a series of fixed cash flows for a series of floating cash flows, where the floating cash flows depend on a variable rate. Sometimes it'll be LIBOR, sometimes it'll be another rate. But anyway, so to price an interest rate swap, to set this problem up, we're going to suppose that time t is today. And we're going to assume that this interest rate swap will have payments that occur at each capital Ti, and the payments will occur at capital T alpha plus 1, capital T alpha plus 2, all the way to capital T beta. So the key here is you can think of T as today's date, and then these big T's will thereby be future payment dates like November of 2016. This could be December of 2016, just any future date. So for interest rate swap, the way to model it is there's two legs of it. So if let's say for example that we are in a receiver interest rate swap. So that means that I'm receiving a fixed cash flow and paying a floating cash flow. So the received cash flow will be this notional N times tau I times K, and the floating leg pays capital N tau I times this floating LIBOR rate right here. And to kind of clarify the notation, this N is the notional amount of the interest rate swap. So it can be, for example, $1 million, and so to get the actual cash payment, if your interest rate was 3%, you just multiply 3% by the notional amount to get the actual cash flow that would occur. Tau I is the year fraction between two payment dates, and this is important because a lot of the times the interest rates, this LIBOR rate here and this fixed swap rate are going to be expressed in annual terms. And so if the payments occur every half a year though, then this tau I would be 0.5, and then you're going to be basically multiplying the interest rate by 0.5. Now K is the swap rate that the fixed party will pay, and then this L, start from Ti minus 1 to Ti, is the floating LIBOR rate that the receiver party will pay to the counterparty. And the key part here is that this LIBOR rate is resetting at time Ti minus 1. And this is actually a really important detail when looking at interest rate swaps, is when the floating rate will reset. But basically, we're saying that if this rate for here example was at 3%, then at time Ti minus 1, that is when we determine what floating rate we're going to be looking at. And that rate will apply for the entire interval Ti minus 1 to Ti. So the next way to look at it is we're going to try to figure out what is the discounted payoff at time t of this interest rate swap. And if we're looking at it from the point of view of time t, we're basically discounting a series of cash flows. And if we're taking it from the point of view of, once again, a receiver interest rate swap, where you're receiving the fixed cash flows and you're paying the floating rate cash flows, then each cash flow at time ti occurs at time ti will be, the K is the receiving rate that you'll get, and then you subtract that floating rate that you're going to be paying. And to go from rates to cash flows, you're going to be multiplying by the N, the notional amount, and then the tau I here. And then this discount factor is basically just present valuing back the cash flows that occur at the big Ti, and you're basically discounting these cash flow payments back to time t. And that's for one cash flow that occurs at time Ti, and then you're summing up across all the cash flows that occur from T alpha plus 1 all the way to T beta. So this is basically giving you the setup of an interest rate swap and how you would think of its value. And I know I'm simplifying little things because interest rate swaps can get really messy in terms of it could be you can add a spread to this floating LIBOR rate, or you can have a gearing factor and all those other things. But ultimately, interest rate swap present value boils down to this type of formula. So once you have the payoff, now it's you're basically pricing any other asset, and you're trying to ask, what is the price of the asset? Well, the key thing here is this is a constant, right? Or this is known today. You know what the discount factor is, and you know the notional amount, and you know these time year fractions, and assuming you know what the swap rate is of that that you entered into, this is the variable rate, because you don't know what the future interest rate will be in 1 year from now, 2 years from now, whatever. And that's really why you're entering into this interest rate swap, is because you're basically you want to receive fixed and pay floating. So this is the random variable here, and whenever you're pricing in any asset with random variables, to get the price, you're basically going to have to calculate the expected value. And we're all already familiar with the risk-neutral pricing. So the present value of the swap can then be phrased as the risk-neutral expected value of this payoff. And I'm just going to basically apply this risk-neutral expectation operator along each component of the sum. So then you'll end up having n, since it's not I-dependent, so you can factor out the sum, of the risk-neutral expected value of each of the cash flows, which is how we get to this formula right here. And for simplicity purposes later on, I'm going to rewrite this LIBOR rate as a forward rate, because the future LIBOR rate at time ti minus 1 really is the forward rate from ti minus 1 to ti at time ti minus 1. And this is really the random, stochastic modeling underlying variable that we're looking at. So that is what is random here. Now the key problem when you're looking at this interest rate swap is right now, whoops, that didn't mean to happen. You don't really know, we can't really break this equation down any further. And the reason why is this underlying variable here, this forward rate that's trying to proxy the LIBOR rate, is not fixed. It is not a martingale. And it boils down to the fact that the risk neutral expected value of this forward rate does not equal the current forward rate for the interest rate going from ti minus 1 to ti. So given all we know today at time t at this field, the conditional expectation of the forward rate at time ti minus 1 for this time period does not equal the forward rate that we can observe actually today. And because of that, we can't really do anything else further. And this is, this basically forces us to get stuck. And this is not a problem when you're looking at call options and where you have our numerator be the discount factor, because for those, we found that the risk neutral expectation of the discounted stock price was a martingale, so that was okay. But here, this underlying random variable, which is the forward rate, is not a martingale under this measure. And this is when we have to utilize this change of measure that is so common when you're looking at interest rate derivatives. And you're thinking, what measure are we going to look at here? Well, if we rewrite this forward rate, so I know that was a lot of information, but we rewrite the forward rate as, in terms of the zero coupon bond prices. So this is the zero coupon bond price at time ti minus 1. This is the zero coupon bond price at time ti. And then you're dividing it by the tau I. So this is just rewriting the equation for the forward rate that I've gone over in a previous video. If we rewrite this and basically do some algebra and re-express this equation here as this, what this tells us is the forward rate times the zero coupon bond price that expires at big TI is the difference of the zero coupon bond prices at time TI minus 1 and times TI. And if you remember from our previous theorem that basically any asset that can be expressed as the price of a tradable asset, if you divide that by another a numerator, then that variable is a martingale under that numerator. So I know that was a lot to take in, but basically F times P right here, this is a tradable asset because it equals the difference of two other tradable assets. The zero coupon bond expiring at time big TI minus 1 and the zero coupon bond expiring at time big TI. So because this is a tradable asset, this entire left side of the equation, if you divide this by the zero coupon bond price at TI, it is a martingale under the numerator PTTI. So this is the key result here that allows us to really price this interest rate swap. and it's under the TI forward measure, which is the numerator associated with the zero coupon bond P little t big TI. And this is important too because it's going to depend on each cash flow, because each cash flow occurs at a different time. So we're going to be using a different change in measure. So for the cash flow that occurs, at another I, we're going to be using the other TI forward measure. So now if we basically scroll down here, my computer is lagging. Sorry for that. Hopefully it's need to get a. This lag has been the bane of my existence recently. I'm gonna scroll down more, but yeah, hopefully that made sense there. The key thing here is under a forward measure where you have the numerator be the zero coupon bond price. This forward rate is now a martingale. Okay, so I don't know why is that. Why is this happening here? This should not be happening. My computer's having some strong lag time right now. Anyway, all right. Well, I'm just gonna. Okay. I'm just gonna have to wait for this a little bit. We're almost done with this video here, but basically, what I have here is we're pricing the swap, and now I'm implementing the risk-neutral change of measure here. So, whereas here, what we saw is where you have the risk-neutral expectation, I'm changing measures now using the numerator of the zero bond price expired time TI. And remember, this is different for each cash flow that occurs because they occur at different times. So now with this change of measure, that DTTI becomes a P little t big TI, and now I can carry this expectation over to the forwarder here. And that is because of the fact that it is now a martingale under that measure. So if I reveal my next little snippet. Oh my god, seriously, my computer is really slow for some reason. This is not the greatest. Okay, there it goes. It was just there. Alright, it's back again. Sorry about that. So as you can see, now I'm distributing the expectation directly to that forward rate. But this is great now because under this measure, this variable right here, this forward rate going from TI minus 1 to TI, is a martingale now. And this basically yields the final coveted pricing result here that allows us to basically just use today's forward rates to price a swap. Ta-da! This expectation of the forward rate go from TI minus 1 to TI at the future big TI minus 1 is simply the forward rate at time t, little t, which is today. And this is a known variable because you can derive the forward rates from today's discount curve. And now, everything here is known. If you have the swap rate is known, the zero coupon bond price is known, the notional is known, and everything is known, and therefore you can calculate the present value of the swap today. And this is how you would implement any kind of pricing of an interest rate swap in C++ program. You basically follow this pricing formula where you have a term structure of interest rates, and you can derive their forward rates, their time, the forward rates today at time t, and price your swap that way. But the key thing here was we had to use a change of measure in order to derive this formula. So hopefully that made sense. Sorry for the little technical difficulties here, and I'll kind of go over the next video on how to calculate what we call forward swap rates. Yeah. Now I'm just trying to close my video.